bubble sort algorithm. Imagine you're organizing your bookshelf and you want the books to be in order from the shortest to the tallest. You start by comparing the first two books. If the first one is taller than the second, you swap them. Then you move on to compare the second and third books, swapping if necessary, and continue this process until you reach the end of the shelf. You repeat these steps, going back to the beginning of the shelf and comparing pairs of books, swapping when needed. Each complete pass through the books pushes the tallest one that hasn't been sorted yet to its correct position, just like a bubble rising to the surface of water. That's why it's called bubble sort. In computer science, we use bubble sort in a similar way to sort data elements like numbers in a list. We compare each pair of adjacent elements, and if they're not in the correct order, we swap them. This process repeats until the whole list is sorted. However, just like it would take a long time to organize a huge bookshelf this way, bubble sort can be quite slow for large sets of data. It's not the most efficient method for sorting big lists, because it involves so many comparisons and swaps. For small or nearly sorted data, it works well enough, but when dealing with lots of data, computer scientists usually prefer faster algorithms. Please pause the video and answer the exam question in your exercise books. Alright, let's talk about merge sort, an efficient general purpose and comparison based sorting algorithm. Imagine you've got a really messy bookshelf. Books are all over the place and you need to organize them by genre, then by author, in a way that you can easily find any book you're looking for. Merge sort would tackle this task in a divide and conquer approach. This means it would first divide the entire shelf into smaller sections, or in computer science terms, it would split a list into halves repeatedly until each little pile has just one book. Once you've got these single book piles, merge sort starts to merge them back together. But here's the catch. As it merges the piles, it makes sure the books are being ordered correctly. So if you're merging by genre, each time you bring two piles together, they become one sorted pile by genre. Now, you repeat this process, combining piles over and over, but each time they're merged, the resulting larger pile remains sorted. It's like putting together a puzzle. You start with individual pieces and merge them into bigger sections until you've got the whole picture. In the end, all the small ordered piles are merged back into one big, neatly organized bookshelf. In the case of a computer algorithm, you'd have a fully sorted list. That's merge sort. It divides the problem into manageable chunks, sorts those, and then combines them back into a complete ordered set. Simple and elegant. Please pause the video and answer the exam question in your exercise books. Algorithm, which is a method used to sort a list of items like numbers or words in order. Imagine you have a hand of playing cards. To sort them, you would start with one card in your hand, then pick up each new card one by one and place it in the right position so that the cards in your hand are always sorted in the context of the image. The list of numbers we want to sort is split into two parts, the sorted part on the left and the unsorted part on the right. At first, the sorted part just has one number because one item by itself is already sorted. The process begins by taking the first number from the unsorted section on the right and comparing it to the numbers in the sorted section on the left to find where it fits in order. This is done with each number in the unsorted section, moving them one by one into the correct position in the sorted section. The steps are repeated for every number until there are no more numbers left in the unsorted section and all numbers are in the sorted section in order. The image shows this process step by step with the numbers 17, 12, 20, 15, and 8. You can see how, with each step, the numbers on the left become more organized. Insertion sort is particularly good when you don't have many numbers to sort. It's simple and doesn't need much additional space. But if you had to sort a whole school's worth of test scores or a big music library, it would take a long time, And you might use a faster method like merge sort. Just like if you were organizing a huge pile of books, you'd want a method that helps you do it quicker than just one by one. Please pause the video and answer the exam question in your exercise books. A linear search, an essential algorithm for anyone getting to grips with computer science. Let's break it down into simpler terms and practical examples. Imagine you have a long line of students in your class and you're trying to find out if your friend Alex is in the line. Starting from the first person in the line, you check each student one by one until you find Alex. This is exactly how a linear search works. It begins with the first data item and moves sequentially through each one until it finds the target item. The slide mentions that the list, or line of students in our example, doesn't need to be in any particular order for a linear search to work. Whether Alex is at the front, middle, or end of the line, you'd still go through each person in order until you find him. However, if the line of students is really long, say hundreds of students, checking each one could take a long time. That's why the slide points out that for large lists, a linear search isn't very efficient. It's simple, but not always the fastest way, especially when dealing with big amounts of data. In computer science, understanding how a linear search works is a good foundation, as you'll encounter many scenarios where you need to find items in a list, and knowing the trade-offs of different search methods is key to choosing. Please pause the video and answer the exam question in your exercise books. Let's talk about binary search in a way that makes it super clear and easy to understand. Imagine you're looking for a specific song in a huge playlist that's sorted alphabetically. You could go through each song one by one, but that would take ages, especially if your song starts with a letter like call. That's where binary search comes in. It's like a shortcut to finding your song without having to listen to each one. Here's how it works. You start in the middle of the playlist. If your song comes alphabetically before the middle song, you know it's in the first half of the playlist. If it's after, it's in the second half. Then you take that half of the playlist and look at the middle song again, repeating the process. Each time you do this, you cut the number of songs you have to look through in half, which makes finding your song way faster. But here's the catch. This only works if your playlist is sorted. If it's all mixed up, you're back to listening to each song one by one until you find yours. So binary search is a smart way to find things quickly in a list that's already organized. It's like flipping to the middle of a textbook to find a chapter instead of reading every page from the start. It's efficient and saves a ton of time, which is why computer scientists love using it for big sets of data. Please pause the video and answer the exam question in your exercise books. SQL is a powerful tool used to communicate with databases. Think of a database like a big organized set of drawers where data is stored. SQL helps us find and work with the data we're interested in, much like if you had a remote control that could instantly open any drawer and show you its contents. In the image, the basic format of an SQL command is shown. The select part is where you specify what information you want to see. It's like telling your remote control exactly what items you want to pull out of the drawers. The from part tells the database which drawer or table to look in. And the where part is like a filter. It tells the database to only show items that meet certain conditions. They've given an example using a cars table, which is like a specific drawer labeled cars that has information on various cars. In this table, each row represents a different car, and the columns have information about the car's make, age, miles, and color. Please pause the video and answer the exam question in your exercise books. The image you've shared shows 3 fundamental logic gates and their respective truth tables. These are essential concepts in computer science, especially when you're studying how computers process information, starting with the NOT logic gate. This gate works on a single input. It simply reverses the signal. If you put in a 0, you get out a 1. And if you put in a 1, you get out a 0. This is called negation. In other words, NOT changes true to false and false to true. Moving on to the AND logic gate. This one takes 2 inputs. It only gives a 1 as an output if both inputs are 1. If either of the inputs is 0, the output is 0. Think of it like a strict security system that only opens the door when both keys are turned at the same time. Lastly, the OR logic gate also takes 2 inputs. It outputs a 1 if at least one of the inputs is 1. If both inputs are 0, then the output is 0. You can compare it to a classroom door that opens if either the teacher or a student has the key. The truth tables below each logic gate symbol show the outputs for all possible combinations of inputs. These tables are a handy reference for understanding or predicting how each gate will behave with different inputs. They're like recipes that tell you exactly what you'll get when you mix certain ingredients together. Understanding these gates is like learning the abs of computer logic, which is the foundation of everything from simple calculators to the smartphone you might be using right now. Please pause the video and answer the exam question in your exercise books. Into the world of arrays using a simple and real-world scenario. Imagine you have a shelf in your room where you can display exactly 5 of your favorite books. This shelf is like an array in computer science. An array is a collection where you can store a certain number of items, in our case, books, and each spot on the shelf has a number, starting from 0, which is called its index. Now, the rule of the shelf R array is that all the items must be the same type. Just as you wouldn't mix books with clothes on the shelf in an array, you can't mix different data types like numbers and text. Here's how you can work with your shelf. To look at each book on your shelf, you'd start from one end and move to the other. In coding, we use a for loop to do this. Let's say you have your books arranged as Scooby, Shaggy, Velma, Daphne, and Fred. Using a for loop, you can look at each book's title one by one. Inserting a book. Suppose you get a new book called Laura. Since your shelf can only hold 5 books, you can't add a 6th one without removing an existing one. However, if you no longer like Daphne, you can replace it with Laura. In an array, you're changing the value at a specific index. This isn't really adding, it's deleting a book. Let's say you don't want to display Shaggy anymore. Your shelf must always have 5 books, so instead you can turn the spine to face the wall, making it like it's not there. In coding, we do something similar by setting an array's value at a certain index to something that signifies it's empty, like a blank space or a special value. Searching the shelf. If you want to find a particular book, say Velma, you'd go through each spot on the shelf until you find it. In programming, we use a loop to go through each element in the array until we find the matching title. By using these operations, you can manage your shelf of books quite effectively, which is similar to how you can manage data in an array when programming.